Okay, well, we'll move right on to Gordan Plotkin's talk once we've wired him.
Seems okay. About to focus on the right. Well, good afternoon. I'm very pleased to be here to have such a pleasant invitation from the Future Conservation Society, whose existence I just recently learned. All facts, which I've known for many years and been pleased to talk about before. It's such a good-looking audience. This is a personal story, unlike previous story, but you'll see from this that personal stories are just part of the crowd, that one interacts with many people. Really, it's a story of interaction. And I might mention that you'll see all the different people who were interacted with over the years, or learned from, even if not personally interacted with. But for me, the person that I learned most from, in the sense of interaction with, is Robin Milner, and his name will come up several times. I just want to mention that ahead of time. It's being a personal story doesn't make me any less liable to the difficulties of history. In fact, it makes me more liable. All I found out, in fact, with this talk is derived from a paper I wrote with the same title, and in writing that paper, I learned only too painfully clearly how bad my memory is. I many times did what John said whenever I thought something might be the case. I sent emails to people and found just wrong. It wasn't like that. It didn't happen. It wasn't in those orders. I didn't think that. You didn't say that. It's all wrong. So whether what I'm saying today is right, it's hopefully a converging process, but I don't make any very strong claims. So although this is about structural operational semantics, it's a long story. Let's see. So the story goes like this. There's a beginning before 1967. That's when I first became a graduate student. And then somehow in that before period, that's the kind of period in which you get a feeling there is some kind of problem, there's something not quite right. There's these interesting techniques, and eventually they kind of come together. And they came together in at least two stages. One I'm calling using rules. I'll explain what it is more later. The next part is concurrency. And then at that point, I realized, oh, this could be done. And that's where the Aarhus lecture notes, which you presumably are largely aware of, they became written at Aarhus, and as part of the Aarhus lectures. And then there's afterwards, which takes us up till now. So that's a very long time. I was looking at this very long time and thinking, that's really terrible, so little done in such a long time. But we might all think that. Okay, so in principle I have 5 slides, but unfortunately each slide has sub-slides. So the first slide, this is the beginnings. So the very beginnings, Rod Burstall taught me lambda calculus, and I learned about abstract syntax from reading the works of McCarthy and Landon. These are very important things. I'm just presuming people know what kinds of things these are. And the SECD machine was very interesting. The whole sequence of papers by Peter Landon are very clearly written. And even if he wasn't here, I would tell everyone to read them. Then there was the Vienna definition language. So the SED machine was okay, but it has its problems. Let's look at how now I can criticize it. Let's see. Suppose we look at the SED machine for a second. Let's see. So it's this little beast here, and it's got stack, the control stack, and dump, and there's transition rules from dumps to dumps. Dumps are just sequences of SEC pairs, and there's different rules for, you look at the control, and depending on what's in the control, you do this or you do that. But the typical thing that you do is, if you look at the rule for application, there you'll see you're just about to look at m applied to n. So you say, oh, that's too much for me. I better look at what to look at first. Better look at m first, then I better look at n. Then once I've finished looking at them, I'll worry about how to do the application. So what you're doing here isn't semantics at all. It's just mucking around with the syntax, trying to find somewhere interesting to happen. And the SED machine does that a lot. It's always wandering over the syntax. But things got a lot worse when it came to trying to upgrade these ideas to PL1 or whatever real language people were interested in. That's just a much more complicated beast. You just need more components, and you just need to have a lot more rules. And somehow or other, the forest has got a lot bigger than any important little seedlings in it, somehow. And that was just personally brought home for me in a seminar in Edinburgh, in which I saw how painful it was, how hard it was, how much work was done to produce these very complicated definitions. So that was a kind of a feeling, there was a kind of a problem there. There was something not quite right. And so what about some nice things that happened? So one nice thing that I came across, and maybe not everyone knows about these things, very nice things of Raymond Smulyan, called his rule systems. And let's see. So here's a little Smulyan rule system, just the top part there. So the idea is it's just really like horn clauses. You're allowed predicates, and predicates or relation symbols can have several arguments, and you just put in strings there, and you draw conclusions. So that says if x, y, z is an S string, and x is an A string, and y is a B string, and z is a C string, then ax, by, cz is an S string. So if being an A string means being a string of A's, etc. for B and C, then this is just part of an axiomatization of the set of all strings in the form A to the n, B to the n, C to the n. So it's a typical context-sensitive language. It just shows the power of Smulyan's system, just one very simple rule. If you try writing context-sensitive grammar for this, you'll be writing an SECD machine 5 seconds later. Okay, you'll have things going all over the place. This kind of gives the idea. Okay, so that was one nice thing. Then another exposure to rule systems was when I came across Henk Barendrecht's thesis in lambda calculus, and he axiomatized reduction just by little rules like that. Actually, I think I've got a slide with more of the rules on it. Let's see. I've got that. Yeah, I just want to show, yeah, I can't remember if this is in Henk's thesis or not, but it's the kind of thing one can do. So if you're interested in normal order evaluation, I don't know if you ever studied lambda calculus, these things are defined. It's really hard work describing all these things, leftmost, outermost, reduction strategies and so on. But what Henk showed, or the tools that Henk demonstrated, enable one very directly to give these things by rules. So you have rules like, just like this, I can evaluate m to n prime, then I can evaluate mn to m prime n, and similar things for evaluating the right, where the left-hand thing is in a special form. And if you take that...
Scanning a bit, Gordon, John moved the projector out. Could you move the projector in?
What, projector in?
Yeah, if you move the projector towards the screen, we'll see all this live.
Oh, right. And up. Still not true what you're saying. There you go. Okay. Thank you. You want to see all the slides? Okay. And it doesn't really matter about the details. The point is that these are just simple rules about lambda terms, and you get a relation arrow, and if you take arrow star, that's exactly normal order reduction. And whether or not that means anything to you, it meant a lot to me at the time, because it was just so hard to define normal order reduction directly. So those were the things, and the hints were rules. So that takes me on to the second slide, which I'm going to call working with rules. So that's it here. So by this time there was a lot of stuff in the air. In fact, John's talk has kind of introduced us to some of that stuff. There was SED machine, there was a lambda calculus, there was continuations, various transforms involving continuations. The SECD machine actually wasn't a lambda calculus, right? If you looked at the lambda calculus, you had beta reduction wouldn't be a thing to do in a kind of call by value regime like SECD. So the lambda calculus and the SECD machine, things weren't quite fitting together. So I wanted to write a paper in which everything fitted together. So that involved, let's see, that involved writing other rules. like this. Okay. So these are called by value lambda calculus rules. It's just like ordinary rules, except whenever you do reduction, lambda xm applied to n must already be fully evaluated. So what you can do is you can twiddle the lambda calculus and get a kind of call by value version of lambda calculus that fits perfectly with the SECD machine. And similarly, you can twiddle the SECD machine and get a call by name machine that fits perfectly well. So in fact, the world is okay. It's just there's different things, and each thing comes in several forms. And that paper put that into great detail. It gave that great detail. So I've written denotational semantics there because what one has to remember, this is kind of post 69, almost like a reaction to all this terrible operational semantics. These very difficult, not difficult, these complicated, let's say, interpreting machines. Denotational semantics was pure, it was mathematical, it was blessed. And so everyone thought that. And so that's what happened here some of the time. The operational semantics was there, but it wasn't particularly remarked on. It's just a tool. And it was a tool you did in order to prove things about your denotational semantics you used. Okay? So, for example, if you take Mike Gordan's thesis, Mike Gordan worked hard and he got a difficult semantics for a difficult language, which was Lisp with, oh God, well, I usually forgot what it was, dynamic binding. Okay, and he gave some operational semantics for that, and he showed that they fitted together. And Jean-Marie Cadieux and John Bielman did similar things for other sort of thing. Then I came back. I don't know how much detail one wants. This was type lambda. This is basically type lambda calculus, and doing a similar thing for that versus a corresponding system of rules. These system of rules are now, you would recognize now as a small step operational semantics for type lambda calculus called by name. Okay, but this was very much a paper looking in great detail at Scott's denotational semantics of the type lambda calculus, which was then a very interesting underground paper. Okay, but one had to teach also, and so teaching these things to undergraduates, you should really simplify, at least make some attempt to get closer to the ground of their experience rather than yours. And so in teaching them, third-year students in Scotland, I taught recursive definitions. Then Robin took over the course and he said, well, actually really imperative programs, assignment and so on is what's important for them. So he did simple imperative language, SIL. Students understood much better this operational semantics than they ever did these fixed points and whatever, and they still do. Outside Edinburgh, this was used a bit too, but not much. In fact, as soon as anyone used it outside Edinburgh, they usually came to Edinburgh, got absorbed. I don't know why. It's a kind of local fixed point. So no one ever heard about this stuff, which is fine, because we could write lots of papers. And we carried on writing papers. But the next period, roughly speaking, I mean everything's really a bit interleaved, but roughly speaking, the next period was getting interested in parallelism, which I mean concurrency, but with imperative things, where you just have procedures or whatever statements going in parallel. So Matthew Hennessy and I did a language for that, but again we're looking at the denotational semantics. Then Robin began his struggles in a series of epic papers on CCS, and at some point he had this idea that he could do, after what?
CCS in this context
yes.
stands for
calculus of something else. Calculus of communicating systems. Yes, CCS means many things in many contexts. Anyway, this is a particular context. Okay, so Robin noticed that if you used Keller's idea of labeled transitions, you didn't just have bare arrows, you put some information on what was happening in the move, namely how you were communicating with the outside world, then you could actually go ahead and write simple rules for CCS. In fact, I know you all know these things, but these rules are so amazing. At least I was so amazed by them, I'll just put them up again. There they are. The main rule, so suppose P and Q are in parallel, then P can communicate with the outside world by itself, that's the first rule. Q can communicate with the outside world by itself, that's the second rule. Or P and Q can communicate with each other, that's the third rule. And you're playing with the actions. You're particularly playing with them in this interaction rule. The third rule, if P does an A action and Q does a complementary A bar action, then the whole thing does an action which is actually just internal, so that's the time. So that was beautiful. In some sense, I have to say that mathematically CCS is hideous. And it's kind of funny that this part is so nice. Not just CCS, concurrency is hideous, but some parts are easy. From a mathematical point of view, it's a difficult subject, is another way to put it. Okay, so once we had Robin's idea, then the way was open just to use it. Okay, so you could define other semantics for similar languages like fragments of Ada, or for example, Tony Hoare's first version of CSP, not as opposed to later ones, the one that was in the CACN journal, and you could start doing things like, suppose I translate one language communication into, for example, are CSP and CCS the same or not? Well, of course they're not the same, but can we translate one into the other, so you could sort of make a translation and prove it was correct relative to these operational semantics. So you could do stuff like that, and we rushed ahead and did things like that, and we did more things. Okay, also I should say, that's important, I should have mentioned, once Robin had that, and of course he had to have other things too, there's a whole story behind by simulation, but that's not really part of this. Off he went to wonderful Aarhus, which let you do what you liked and just tell other people about it for 6 months. Of course nowadays you guys can do it for 5 years, but 6 months is enough, said jealously. Okay, so by the time you got to this, the point about Robin's experience was that you could sort of forget about denotational semantics for many purposes. You could just do operational semantics. And in fact, denotational semantics quite often felt more complicated than the operational semantics. So I thought, I could take that seriously. Let's really do that. Let's look at the operational semantics of programming languages just per se as an activity by itself without any other purpose of relating to denotational semantics in mind. So that's the end of the third slide. So I went off to Aarhus and I gave some lectures. I gave quite a lot of lectures. These were great lectures, these Aarhus lectures. They were all 2 times 45 minutes. So you had 45 minutes, then everyone would go for coffee, and then not everyone came back after coffee. That was one of the main purposes of coffee. And then you had I had to go back after coffee and give the remaining 45 minutes. So that was 9 times 2 times 45 minutes, this particular course. It's worth 20 points each in the modern system. So in fact, the first 3, the first 5, if you miss out, apart from 4, the first 5 lectures are what became the Aarhus notes. The other stuff never got written up and never got incorporated. I'm not sure how much I want to say about what that was. This was just, as it were, talking about the SECD machine and making the propaganda that this is not where we want to be. And then there was this idea that, although denotational semantics, as it were, was not being done, the ideas, the semantic ideas or the linguistic ideas of that were very much developed in the course of developing denotational semantics were absolutely important. Without those ideas, this could never have been done. So, and those in turn were based on ideas by Strachey and Landon and other people. It's just that whole community of ideas was important here. So ideas like programming language, you think of expressions, you think of commands, you think of definitions, you think of how they're put together. And so that enabled the kind of structuring of these things. So you can see, you start off with simple expressions and simple commands. This idea of using simple calculi, which came from Robin, which is still a very important idea, and definitions, declarations. Type checking was done in there. It was done in an unremarked way, and it went very smoothly. And I always find it a bit weird that this chapter hasn't had more influence than I think it has. I think that was good work, if I may say so. Tried to do a real language and got to a certain point and got tired. I can't remember what happened there. Function procedures, that's whatever it was. Parallelism with shared resources, that was stuff like concurrency, monitors, all that kind of thing. Communicating processes were CCS-like things. Just for fun, I did CCS with several means of communication. You could have sort of broadcasting, or you could have stacks in between, just to show that the technique was versatile. You didn't need to be doing synchronous, asynchronous, synchronized communications, handshake communications. The technique would extend to anything. It really was very versatile. And hardware description languages, they're quite difficult, and they've got a sort of odd thing about micromoves in them. That was interesting because Mike Gordan came at Edinburgh, then Cambridge was getting interested in hardware at that time. And finally something in types, abstract types, and polymorphism. And I don't have anything very remarkable to say about that. But in doing these lectures, the various themes, I'd like to mention some of the themes. Oh, I might put up a slide like this. Let's see. Well, just want to put up a slide because this was a slide from the Aarhus lectures. Just anything historian might do. So it's a typical slide. This one's talking about simultaneous definitions and saying if you've got two definitions, D0 and D1, you can put them together and try to explain it to students in terms of information flow. This is stuff flowing into the definitions and definitions flowing out. And the arrows show all the ways the information could go. And this is a private one. The D0 is private definition within D1. So anything, for example, going out of D0 and not going into D1 just gets cut off. The environment doesn't get to see it. So these ideas are several ways of combining definitions which were given there. Okay. So let me just make some remarks. So these were the kind of themes that went through the. How are we doing? No, 10 past 3. It's going very fast.
Oh, you started a bit early. So.
Yeah. Okay. I think it goes so fast. Okay. So themes, remarks. What kind of lessons or themes are learned in this process? So, I mean, if you remember, the problem with the VDM was the states just got VDM. First one. L. Thank you. Problem with VDM. That's one of the problems. The second problem was that you had such a big state. That's what I was talking about before. So the good thing about operational semantics was you got a small state, but you had to. But still, there was a problem, which is where is the action? So in VDL, you chased around, and so here the chasing around is still done there. It's done by the rules, so it's still done. It's done more elegantly, you might say. It was important for me that it was structural and direct explanation. If you look at natural language explanations of semantics, I wanted the formal thing to be close to that, somehow. I mean, I don't know what close means, but somehow it felt closer one way than it feels another. And hopefully that's better for teaching, and it's also better for science. So although they weren't compositional, they were syntax directed. They gave us somehow a direct explanation of operational meaning. So that there's a particular mathematical way to say that, which I want to put up. And so these came from some slides which I found this morning. I was looking through some slides. I found an account of operational semantics dated 1984, given by me in a place called Newborg, which I had no idea where it was. I totally didn't remember these. Anyway, but they're good slides.
I can remind you about the conference later.
Thank you. Yeah. I actually already asked Peter, so I know where it is now. But the funny experience is just a beautiful demonstration of how bad memory is. Like, what was that event? Where is that place? Who knows? So anyway, so if you look, here's compositionality. A given, my goodness, what's that? Let's see. So if you look at trans E of sigma, so given the expression E, and you start, well, the way the definition of trans E is given in a state sigma, you can look at all the configurations gamma that you can get to in one move starting from E and sigma. So this is just a complicated way of saying the operational semantics of E. E is something that, given a state, gives you a set of possible successors. So that set is in fact defined, it's not defined compositionally in E. For example, even the transitions of E1 plus E2. Typical transition of E1 plus E2 is you leave E2 alone, you make a move of E1. So that's not a function of the transitions of E1 and the transitions of E2. It's a function of the transitions of E1 and E2. Okay? But it is, in a different form, it can be written in that way, and that way is a typical example of structural induction, which is a generalization to abstract syntax of primitive recursion. Okay. So that's why I use the word structural. So all the rules, if you look at them, are in this form. It's not quite compositional, but it's almost composition. Okay. So that's one lesson. Use the linguistic ideas in the denotational semantics community, I said. So, for example, I've already mentioned some of them. I could mention another influence. Let's see. Oops. So you know this thing in denotational semantics that you have an environment and variables denote stuff like locations. and locations mean things like values. Okay, so you just have syntactical analogues of that, direct syntactical analogues of that in operational semantics. The variables denote denotable values, and they are usually given by closed state. So what's going on here? Well, actually, no, they still give you locations, or sometimes they can give you closed statements instead of values. So whereas in the Oxford thing you have notable values, in the Aarhus thing you'd have syntactical representatives of them. So you still did exactly the same thing, but you did it, as it were, through with a syntactic eye. Another thing which I paid attention to at the time was advice of Bob Tennant. Let's see. And he had several principles. Let's see. So he had his principle of abstraction, his principle of correspondence, and his principle of qualification. You may have had, I can't remember, it's a nice book called, I think it's called Some of the Principles of Programming Languages. I can't quite remember. Anyway, abstraction, principle of abstraction says that to any parameter calling mechanism, there's a corresponding declaration mechanism, and vice versa. They're one-to-one corresponding. Okay? So, sorry, that's the principle of correspondence. The principle of abstraction says that you can abstract on any, you can do an abstraction on any programming class, a syntactic class, to get something interesting. So if you do an abstraction on expressions, you get functions. If you do an abstraction on statements, you get procedures. If you do an abstraction on modules, you get classes. So that seemed like a nice uniform thing. A very simple principle of correspondence is it doesn't matter too much what principle of qualification is. So that was useful for me at the time. But thinking about this, I realized maybe this is kind of crazy, because anyway, Landon before that, and Reynolds afterwards said, it's the type, well, I didn't say that, but the message I took from it is, it's the type lambda calculus, stupid. In fact, it's the typed type lambda calculus, in fact. So, in fact, all that's going on is expressions are expressions of a certain type. Statements are statements of type unity. You know, all they do is side effects. And modules are things of type record type. And so classes are just functions from the argument type to record type and so forth. But, I mean, I think you explained something like that in one of your papers, I remember. Yeah, I can't remember which one. So, yeah, so because of this thing, I tend to hesitate between looking at programming languages. Actually, maybe I'll come back to that when it gets more dramatic later. Okay, so that's one. So that's usually, recursion caused me a mess about that. I don't want to say too much. Static semantics, I already said something about. Jumps were something that weren't done there, and jumps were done well in VDM. Is that right? No, both. Okay. The VDL and VDM had this kind of what I call trapexis semantics. Instead of continuations, that seems to be obviously the right way to do it. Continuation is obviously wrong. So, when I can't think of a rational argument, you make a strong statement. It seems clear. And so Hannah Rice and Fleming Nielsen, as it were, carried out that exercise of using that idea in the context of operational semantics, and they showed in a master's project, which I was working with them on, that all the ideas went through perfectly well, although that's not in the notes. Just a remark on that. Okay, so that's that. How about afterwards? Let's see. Well, let's see. So afterwards, in some sense, I don't really know. The subject's gotten too big. So one of the things I thought I would do this afternoon is advertise Google Scholar, for those of you who haven't come across it. It's this absolutely fantastic thing. It's like the next citation index, you know, with even more, very fast, immediate response to all kinds of search terms across the whole of science. So you can type anything into it, and well, you get all kinds of stuff fast. You get rid of lots of rubbish. You get all the citations. So if you type structural operational semantics into it, you get about 46,000 citations. So there's a lot out there. I don't know what it is. But so here are some things that happened. So more or less immediately after my Aarhus note, Gilles Kahn was thinking about them, and he emphasized the idea of big step operational semantics. So for me, I was basically trying to do the SCCD machine, but only axiomatize the important arrows. All the other ones I was trying to get rid of. But all the important arrows in the SCCD machine are just one step in the sequence longer. So So Gilles said, well, you could just axiomatise one step star all the way to the end. And so he gave that. And sort of an independent fact about that was that he then implemented that with his colleagues, and that's been a long-standing thing. And so that was a kind of a first tool along these lines. Independently, Martin Liff, in fact, before Aarhus 1979, at least this is the publication date, in explaining his type theory, gave, although in English, a completely clear rule-based account of his type theory, and it was big step semantics. And as John has pointed out, what is an invention? I mean, Robin, for example, writing his CCS book, says if you look at Van Wijngaarden's explanation of the semantics of algol, which one? 68, gave, although in English, a completely clear rule-based account. So maybe it was Van Wijngaarden as the origin of these things. Who knows? Anyhow, so that's the point about big step semantics. Between big step and small step, there's the issue of type safety. That comes up, for example, in type safe machine languages. That's an area of current research. And then just the idea of type safety works is important there, because type safety means you're not writing to bad bits of memory, or whatever it means in different contexts. But that works better, so it seems, with small step and big step. So you have that kind of contrast. Small state, small step, big step. I've already said it's a standard methodology. You can do real languages like W3CX query language by Phil Wardler and so on. They're doing the semantics that way. There's other languages being done. There's a bunch of tools being developed for it, but far too few tools, in my feeling. There's still very much more that could be done, but some things have been done. And concurrency theory's gotten an awful lot further. They have all these formats now, so you can actually write down. You know that if there's a certain format of rules, and if rules are written in that format, then you know that they have certain very nice properties with respect to bisimulation and whatever. So there's quite a lot of theory there. There's an absolutely beautiful idea, which I think this is a major one, well worth pausing on, the idea of evaluation context by Matthias Verleisen. And this exactly comes back to the same point again and again. What he does, evaluation context tell you exactly where in the term the action is. So another way to do operational semantics is I just tell you the evaluation context, and I tell you the single rule for what the action is. So for lambda calculus, basically, the only thing I tell you about the lambda calculus is that lambda x m n reduces to n substituted for x and m. I tell you nothing else. I don't need to give you all these rules. I don't need to give you the SECD machine. That's it. Well, plus the evaluation context. That's a simple recursive definition. So this is a very beautiful idea, and I think it needs to be much more exploited. So it's generally a theory of control points. I mean, how would that work for concurrency, for example? We have several control points at one time floating around. It's not so clear. So that's a good thing. Another thing that's happened in recent years is what I call back to mathematics. Let's see, I've got a bit of time for this. So, I don't, how much time do you have? Plenty, okay, plenty of time.
It's dangerous to say.
Yes. So I mean, one of the things about doing syntax well is it requires really good taste to do it well. For example, we saw Van Wijngaarden, just I can always take as a canonical example, someone not in the room, displays excellent taste. And if you just, or Robin, and if you just display the least bit of bad taste, you just get into total disaster very quickly. You make a big mess, and you enjoy yourself. You think that all you're doing is suffering from the big mess that you make. So mathematics lets you get away from that by looking at structure. So I just wanted to mention a couple of pieces of mathematics people are doing. So one idea is that you can replace transition systems by coalgebras. I'll explain that to you in a few lines. So, and in fact, it was already, this is a direct mathematization of this idea of what it is that one is defining structurally. This is a direct definition of it. What it is the behavior. So the behavior of an expression is the function which, well, actually this is going to be a different one, but I'll just go back to the previous one. It's the function which, given a state, tells you, or store, tells you the possible pairs of successor expressions and stores. And here, the behavior of a CCS program P is a function which, to an action A, tells you the set of possible successor CCS things. So what is that? What is this thing mathematically? Well, mathematically, that's a function from A, the set of actions, to sets of things, so power set of p's, where this p really means the set of all p's. Sorry. So what we have, so another way to write the transition semantics like this is to just give you a function from processes to functions from A to sets of processes. Okay, so this stuff on the right is of the form b of x, where b is defined as p of x to the a. So this b is what people call a behavior functor. So we have a function from p to b of p, and that's called a coalgebra. Just because functions from b of p to p are called algebras. So, and that's a very powerful thing. If you want to know what would be the right form of operational semantics for mixed non-determinism and probability with a bit of communication, you could either invent it or you could write down one of these things, and you can go backwards and forwards. Okay? And various people like Bart Jacobs and Jan Rutten and Daniele Turi, all in Amsterdam, or more or less in Amsterdam at that time, have been and continue to explore these ideas. And you, for example, you can get a general definition of bisimulation there, which covers not only, this is all strong bisimulation, covers not only Robin and David Park's original ideas, but for example, any of the extensions to probabilistic transition systems or anything else. You can do that since, or you can do this in the bicarpets, wherever you like. So that's coalgebras. Another example is algebras and syntax. Think of the definition of processes. So a process is either a pair of processes put in parallel, or a process in which you exclude some name, alpha, or whatever it is. This is the syntax of CCS. I'm just writing that down as a random, well, it's a consistent but essentially random choice. So what does that give you? Well, that tells you every time you've got a pair of processes, I can give you a process. Namely, if you give me P and Q, I can give you P parallel Q. Or every time I have a name and a process, I can give you a process. I just use this syntactic construct. And so that's something squared plus names times something plus something. And this subset is actually a function. It's rather a trivial function, but it is a function going from left to right. And so that gives you a function from sigma x to x, where x is processes and sigma of x is x squared, that's the square, names cross plus whatever. So syntax is an algebra. This is a kind of an algebraic formulation of abstract syntax, starting off with McCarthy and Landon, and then going through the ADJ thing, and this is just a categorical version of the ADJ idea. But look, we're going to have algebras for the syntax, we're going to have coalgebras for the behavior, so we have both together. So I had this idea with Daniele of looking at bialgebras in which you've got both things together. And once you've got bialgebras, the formats turn out to be exactly functions like this. So the idea is, for example, suppose I want to give you the semantics for parallel construct. So this, the part of sigma to do with that is the square. So that means I've got two of these things. So for each process, so I've got two processes P and Q, and so for the P, I know that I've got the P, and I've got the set of moves it can make. That's encoded in the B, and I've got the same thing for the Q. So given that, I can get all the transitions for P parallel Q. So all transitions is given by B, and what you get after that are some terms to do with P and Q. Actually, it's just P prime parallel Q prime, whichever are the simple ones, but in principle, it could be complex. So T just means the set of all terms you can make up from X's, whereas sigma means the terms you can make up by applying one syntactic constructor. This means the terms you can make up by applying any number of syntactic constructors. So you exactly get functions of this kind. And there's a theorem that these functions of this kind, subject to some conditions, are in one-to-one correspondence with the GSOS format, okay, which is a known format for handling this kind of thing. But the point is then that that's a machine, you can turn it. You just replace B by something with probabilities and sigma by something else, and you'll get some other format. And so this gives you a systematic way of looking at things. So I want to say that sometimes there is use for mathematics. So sometimes there isn't. Okay, so just to finish and find my last two slides. So these lecture notes I found this morning had some conclusions too. This was in 1984. This is what I was hoping for in 1984. So it'd be interesting to see hopes, parentheses 1984, versus realities of the present day. So I certainly wanted to see some real languages done. And we have seen real languages done, and we know now in principle that's fine. You can do all real languages. How prettily you can do them, I don't know. And what does prettily mean? So this comes from a concern that Peter Moss has very much put to front of his research over all the years. You don't just want to write down a zillion rules and go home feeling happy. We do want to go home feeling happy, but we should have done it not just completely in order, but at least it should be readable by other than the writers for a few moments. They should be natural. It should be a direct explanation of the denotational semantics. And this is getting hard. It should be modifiable. As soon as you change language a bit, there should be a small change in the semantics, which still makes the whole thing equally naturally readable and complete. And it should be extendable. Okay, so in some sense that feels really difficult because we still haven't done it at all because programming languages are so big. But I've still got this feeling actually programming languages are really tiny. They're just lambda calculi with arranged of a few interesting type facilities, a few orthogonal features, and a few effects. And any programming language is either crappy or it can be has such a small target language as a core sublanguage. And I have no idea what the truth is. I just have both feelings. I'd be interested to hear people's opinions. So I don't know if there's a real problem or a false problem, in other words. Formalization, what's that? Oh yes, I wanted to do the mathematics of it. I didn't know what the mathematics was, but we certainly did a lot more mathematics on that, thanks mainly to the process algebra community. And we're only beginning now to see people extending these ideas from process calculi to, say, imperative programming. So formats for imperative programming are coming out, out of the Netherlands. Some student in, I forget who's doing that. Useful software tools, we need a lot more. There's quite a bit being done since then. I have a list somewhere, but it still doesn't look at all like the ideas are really being exploited. They really need to be exploited. So I'll leave it there. I still have all of these hopes, really, but maybe slightly modified. I wonder if people would suggest these are the right hopes, the wrong hopes, or some missing hopes. Thanks.
Or even Big Step SOS address describing first-class continuations.
Oh, I see. I don't know.
John?
It shouldn't be hard or anything, so hopefully.
I don't know. It is SOS, isn't it? I mean, are you talking
Yeah,
about
that's
license
true.
semantics? It's an example of SOS, I would think.
No, there's some nasty rules in which you have the whole context and embedded in some place and you have to pull the whole context in, so it's not quite so.
It goes by decomposing terms into a context and a plug into the context, and then just defining the reduction rules at the level of the things that are plugged in.
Yeah.
But
I mean, the experience suggests one could do something. I don't think we should know the answer.
Make a nice bridge between the two talks.
Yeah. So you mentioned the various kinds of semantics from the early days, which had extra stuff in them. I think, like the SECD machine.
Oh yeah.
There was fairly pretty interpreters around at that time, weren't there?
And people wrote
lists. Very pretty interpreters, which didn't have too much extra stuff. I was just wondering if they influenced you at all, or if you would comment.
I read about them. I felt negatively towards them. I thought I like to do mathematics and defining things in terms of themselves.
That's true. I was only asking so they didn't. Yeah. It seems to me like reading them now, it's as if they were big step semantics.
Well, that's true, of course, yes. Now, you can read things through different spectacles. That's the point. To some extent, there are spectacles that are changing. Yeah, this gentleman.
Is there any evidence from where you're standing that the work of the last 40 years or so in these fields has had any influence on the kind of notations used out in industry for everyday programming, or do you just look at the world of Java and C# and weep?
Referring to Cliff for industrial
Thanks. Actually, if you don't mind, I have a related question.
Actually, I don't feel I'm properly expert to comment, that's why. So I don't want to invent a comment.
Tobias Nipkow has written down an operational semantics for Java, or most of Java.
Sure.
The question I want to ask you is, The trick which he has pulled, I think, is very clever. I think Tom Mellon was probably the originator of it, which is to take the rules and add them to the holological frame, so that you can essentially do deductions about the relation between states and states, text and states, and states and so on. Do you think that would answer any of your desire for a tool to work with operational semantics?
Yeah, sure. I mean, that definitely does. I mean, I don't think it's today's first thing. It was people at the CMU. Anyway.
Okay.
Yeah,
The earliest reference I know is Tom Mellon's, but maybe other people know earlier.
Your structured operational semantics has been extremely influential. If one writes a paper giving a denotational semantics to a language, inevitably the reviewers will ask what's the operational semantics. On the other hand, if you present structured operational semantics to a language, they never ask for a denotational semantics. I'd like you to comment on that.
Small laughs. I mean, I don't. What kind of comment will you ask? I have no sense of victory. Is that? I'm not even. Is it a good thing? It's a habit, anyway. Whether it's good or not, I think it rather depends on the content of the paper. I mean, the point of the paper. I think there should be a uniform.
I mean, does it mean that it's all too easy to create bad languages because all you expect it to do is write an operational semantics?
No, you can write crappy denotational semantics too. You can work with any bad idea. Do you think? I think actually operational semantics you might do better off with actually. It's simple enough you can see the awfulness more clearly. If you're not trained, if you're trained, you can see they're very much the same denotational and operational semantics. Good. Yeah.
Louder though, John.
All right. I've had some experience teaching operational semantics and denotational semantics to the same groups of students in the course, and I must admit I am taken back by the variety of mistakes they can make in operational semantics.
Yeah.
Where you will show them an operational semantics of a language, explain what the operational semantics means, and then give them minor extensions to the language as problems. And you will get back things that not only are not correct answers to the problems, but which are not definitions of any conceivable language. Completely wrong.
Yeah,
And you get this much more frequently with the operational semantics. I don't see
The students probably couldn't write denotational semantics of any kind in the first place. So.
No, but I think I agree. I think the people find it easier to understand mathematical structure.
Yeah.
Therefore, the denotational semantics is easier to set up.
It's easier.
Yeah, I find it.
It depends where you're coming from, it really does. The actual mathematics for operational semantics is obviously much more elementary.
If you describe the structural operational semantic rule for a new structure, you have to think about everything that happens in the machine. You have to build extensions to the memory model to make sure that everything that you want to represent actually sits there. And that's a complicated thing. Much more complicated in structural operational semantics than in denotation semantics.
Okay, maybe. I feel they're very close. I mean, I've always been interested in people showing how close they are. I'm not.
I guess the question, this partly is an answer to the question about industrial languages. I think the problem is that semanticists, I've said this before obviously, should be the obstetricians and not the coroners of programming languages. And we spend too much time trying to describe languages that show extreme signs of amateur construction. And it is time that we struck out our own dictation and tried to design programming languages that are easy to use. That has two good effects. One is that the languages could come out of it, and the other is that we might learn a few things. semantic systems have been used to define all the warts of languages, including things that everyone generally acknowledges as a wart. And my viewpoint is that if a semantic method can easily define a horrible wart, then it is a bad semantic method. What I dream of is a semantic method so good that it will just tell you what the programming language looks like, and that'll be that. I don't know how to do it.
You might not get that, but you might get a remeasuring complexity of the definition. These words tend to complex definitions, for example, typically nasty recursions. Sorry, actually, Cliff, the gentleman.
Oh, sorry,
yeah,
yeah.
I don't know if you wanted.
Yeah, what I was trying to say was, in your hopes you mentioned that you want to apply for a real language. So,
What?
in your hopes, the last slide,
Yes.
you mentioned that you want to apply it to some real language.
Well, those were 1984 hopes.
Okay.
It's been done. That was okay. Yeah.
But my thought was, well, in what way will the operation semantics or denotational semantics will have impact on an existing language or even on a language which you want to design? I mean, can you identify some flaws in existing languages or?
Well, I think you can look at it. I think the ML experience shows those kinds of things actually happening in practice.
Okay.
And I bet the same is true of this W3C thing. I don't know the story well enough. I should ask Phil. But just for the reasons, so it's a kind of dynamic version of the question that was being asked here more statically. Yeah.
So I agree with you that one of the huge payoffs of operational semantics is with concurrency. So you know what's coming next. How do you feel about your work on power domains, which was an attempt to give a denotational semantics to concurrency?
Well, anticipating this question because he told me it's going to come, I looked it up in Google Scholar. And I found 490 references. So therefore, I would conclude power domains are 100 times less important. Or do you want a longer answer?
Very precise.
Pardon?
Very precise.
This is exactly, yeah, it's a superb system. Yeah, I have a longer answer, but
Overdid it.
yeah.
So you mentioned big step semantics versus small step, and one of your mentors, Robin, used big step for defining ML.
Right.
What, in your view, are the trade-offs between which to choose and which purpose?
That's a really good question. So I know for type safety, I talked to the people and I thought about it. It really seems you don't get to get the right theorems, you have to use the small step semantics. And on my feet, I don't usually remember. It's a simple point. I can't quite remember.
Also, big step tends to require non-inductive rules when dealing with iteration and procedures.
Well, it's just that with type safety, you want to show that nothing goes wrong during computation. And to show that during computation means every single small step. So actually doing the mathematics works better there. Big step semantics feels more like denotational semantics. Just what denotational semantics is, it's more of a global thing. It takes you straight to the end. So if you really want to know what's happening locally, you should be looking at small step semantics.
It ignores non-termination as well, of course.
Yes, there's always non-termination as well.
Well, Cousteau, I think, had a more advanced framework that did take account of non-termination.
With big step semantics?
Well, when transfinite or something, I forget the details.
Yeah, you can add another predicate for termination and so forth. But a really thorough answer to your question, I wish I had it initially. I somehow feel that operationally, somehow you should be explaining every step. It's more in the spirit of operational semantics to do the small steps. But that's a kind of, more of a kind of feeling type of answer.
I can give you a concrete.
Yes. I mean, so one reason I didn't do it was to look at the rule for whiles.
Yeah.
Then that's not structural. I want
Exactly,
to
yes.
structural.
Yeah. So that's one reason. Another is that you can give a modular semantics for exception handling using a small step style that I don't think you can in the big step style. So that might be actually a way of using one of your desiderata for justifying a small step.
Yeah. Okay. So it needs some thought.
Okay.
No.
I'd like to ask what happened to Van Wijngaarden grammars, and were they relevant when the static semantics were very complex, and did we go to languages where static semantics were simpler, and therefore we could look more at the dynamic behavior?
I've got an answer inside me somewhere. They're very important. Well, let me try to remember my answer and tell you. I can't quite remember what it is. That's another kind of thing. I can't quite remember what one it was, but we'll come back.
I'm thinking about small steps in semantics.
Yeah.
I think that's good for implementation.
Oh yes, yes. That's another point. You get closer to implementers.
And big step probably good for interpretation.
Yes, that's right. And closer to logic. And similarly, going back to SECD machine and abstract interpreting machines, these are the kinds of things that are more close to, that's even closer to implementation. So everything depends what you're trying to do. If you're trying to write semantics for someone to understand is one thing. If you're trying to write things for efficient implementation is another thing. And you need to expect the same things to be the right answer to different questions. So abstract machines are very interesting, to study also. And there should be a general theory of abstract machines, and there isn't. There's two more questions, but Dan.
The operational semantics and denotational semantics, were they developed to address the same kind of issues, or they had originally different motivation? I'm thinking maybe more programming language definitions versus reasoning about programming or something like that.
I think they were almost direct competitors, to be honest.
And the main motivation was about programming language definition?
Yeah, unless I'm very wrong. Of course, denotational semantics per se has an independent history in logic.
Yeah, that's why I'm asking.
Yes. But there's no corresponding notion of operational semantics in logic. Though there is an interesting question about intuitionistic attitudes to things, to natural language, which gets closer to operational semantics, isn't it? It's never been well developed. If you look at Arne Ranta's work, for example, he does type theoretic semantics of natural language. There are things that could be said, but just in regards to straight historical answer to your question, I think they were trying to do the same things as their direct competitors, to my understanding. Oh, same question, yes. Okay.
Okay, let's break there, 20-minute break.